Many authors, for example, Dreyfus and Dreyfus 1985 and Winograd and Flores 1986, have drawn on Wittgenstein's and Husserl-Heidegger work in their criticisms of AI. Although many AI practitioners continue developing the rational logical agenda, also known as GOFAI, or good old-fashioned AI, a growing number of researchers in the field have incorporated these criticisms into new and exciting models of intelligence. In keeping with Wittgenstein's emphasis on anthropological and cultural roots of knowledge, they have turned to social, sometimes referred to as agent-based or situated models of intelligent behavior for their inspiration. As an example of an alternative to a logic-based approach, research in connectionist learning de-emphasizes logic and the functioning of the rational mind in an attempt to achieve intelligence by modeling the architecture of the physical brain. Neural models of intelligence emphasize the brain's ability to adapt to the world in which it is situated, by modifying the relationships between individual neurons. Rather than representing knowledge in explicit logical sentences, they capture it implicitly, as a property of patterns of relationships. Another biologically based model of intelligence takes its inspiration from the process by which entire species adapt to their surroundings. Work in artificial life and genetic algorithms applies the principles of biological evolution to the problems of finding solution to difficult problems. These programs do not solve problems by reasoning logically about them. Rather, they spawn populations of competing candidate solutions and drive them to evolve ever better solutions through a process patterned after biological evolution. Poor candidate solutions tend to die out, while those that show the promise for solving a problem survive and reproduce by constructing new solutions out of components of their successful parents. Social systems provide another metaphor for intelligence in that they exhibit global behaviors that enable them to solve problems that would confound any of their individual members. For example, although no individual could accurately predict the number of loaves of bread to be consumed in New York City on a given day, the entire system of New York bakeries does an excellent job of keeping the city stocked with bread, and doing so with a minimal waste. The stock market does an excellent job of setting the relative values of hundreds of companies, even though each individual investor has only limited knowledge of a few companies. A final example comes from modern science. Individuals located in universities, industry, or government environments focus on common problems. With conferences and journals as the main communication media, problems important to society at large are attacked and solved by individual agents, working semi-independently. Although progress in many instances is also driven by funding agencies. These examples share two themes. First, the view of intelligence as rooted in culture and society, and, as a consequence, emergent. The second theme is that intelligence is reflected by the collective behaviors of large numbers of very simple, interacting semi-autonomous individuals, or agents. Although these agents are neural cells, individual members of a species, or a single person in a society, their interactions produce intelligence. What are the main themes supporting an agent-oriented and emergent view of intelligence? They include 1. Agents are autonomous or semi-autonomous. That is, each agent has certain responsibilities in problem solving with little or no knowledge of either what other agents do or how they do it. Each agent does its own independent piece of problem solving and either produces a result itself, does something, or reports results back to others in the community. Communicating agents. 2. Agents are situated. Each agent is sensitive to its own surrounding environment and usually has no knowledge of the full domain of all agents. Thus, an agent's knowledge is limited to the tasks to hand. The file I'm processing or the wall next to me, with no knowledge of the total range of files or physical constraints in the problem-solving task. 3. Agents are interactional. That is, they form a collection of individuals that cooperate on a particular task. In this sense, they may be seen as a society, and as with human society, knowledge, skills, and responsibilities, even when seen as collective, are distributed across the population of individuals. 4. The society of agents is structured. In most views of agent-oriented problem solving, each individual, although having its own unique environment and skill set, will coordinate with other agents in the overall problem solving. Thus, a final solution will not only be seen as collective, but also as cooperative. 5. Finally, the phenomenon of intelligence in this environment is emergent. Although individual agents are seen as possessing sets of skills and responsibilities, the overall cooperative result can be viewed as greater than the sum of its individual contributions. Intelligence is seen as a phenomenon resident in and emerging from a society, and not just a property of individual agent. Based on these observations, we define an agent as an element of a society that can perceive, often limited, aspects of its environment, and affect that environment either directly or through cooperation with other agents. Most intelligent solutions require a variety of agents. These include rote agents that simply capture and communicate pieces of information, coordination agents that can support the interactions between other agents, search agents that can examine multiple pieces of information and return some chosen bit of it, learning agents that can examine collections of information and form concepts or generalizations, and decision agents that can both dispatch tasks and come to conclusions in the light of limited information and processing. Going back to an older definition of intelligence, agents can be seen as the mechanisms supporting decision-making in the context of limited processing resources. The main requisites for designing and building such a society are 1. Structures for the representation of information. 2. Strategies for the search through alternative solutions. And 3. The creation of architectures that can support the interaction of agents. The remaining lectures of this course include prescriptions for the construction of support tools for this society of agents, as well as many examples of agent-based problem solving. Our preliminary discussion of the possibility of a theory of automated intelligence is in no way intended to overstate the progress made to date or to minimize the work that lies ahead. As we emphasize throughout this course, it is important to be aware of our limitations and to be honest about our successes. For example, there have been only limited results with programs that in any interesting sense can be said to learn. Our accomplishments in modeling the semantic complexities of a neural language, such as English, have also been very modest. Even fundamental issues such as organizing knowledge or fully managing the complexity and correctness of a very large computer programs, such as large knowledge bases, require considerable further research. Knowledge-based systems, though they have achieved marketable engineering successes, still have many limitations in the quality and generality of their reasoning. These include their inability to perform common-sense reasoning or to exhibit knowledge of rudimentary physical reality, such as how things change over time. But we must maintain a reasonable perspective. It is easy to overlook the accomplishments of artificial intelligence when honestly facing the work that remains. In the next section, we establish this perspective through an overview of several important areas of artificial intelligence research and development.